Alright, so today's lesson is 6.3 from the Sullivan textbook on exponential functions. Our objective is that I can evaluate and graph exponential functions. The majority, if not all, of what we're going to cover today really is just going to be review. It's setting us up to get ready to build on what the inverse of an exponential function is. So yesterday we talked about inverses. Today we'll talk about exponential functions, and then we'll move on to actually talk about what the inverse of an exponential function is. I like to start by just reviewing with you some of the laws of exponents. So this is not something that you need to copy down, but if you'd like to, you can go ahead and pause this video and write these down. Just want to quickly review some things with you on laws of exponents. So if you look at the first one here, a to the s times a to the t, when you're multiplying with the same base, you're going to go ahead and add the exponents. Here is when you have a power raised to a power, you multiply the exponents. When you have two things that are multiplied inside a parenthesis and they're raised to the same exponent, it's as if each one individually was raised to that power and then multiplied together. I do want you to notice though that there's not a plus sign between this a and b. If there was a plus sign, then it would be more of the case where we have to write the quantity more than once and use distributive property. Here's just a reminder that 1 to any power will still be 1. Any base to the 0 power is always 1. And when I have a negative exponent, the way to change it to positive is to use the reciprocal. And because the numerator, at least in this case, is 1, it would be the same thing as if the power was outside of the entire fraction. So just a quick review on that. Also just a review of the definition. No need to copy this. It says an exponential function is a function of the form f of x equals a to the x, where a is a positive real number and a cannot equal 1. The domain of f is all real numbers. So in order for something to be an exponential function, we're seeing that the variable is in the exponent, not the base. So the base is going to give us a constant or just a positive real number, and our exponent is, we're finding in the, our exponent is a variable. Notice here it says the base is not going to be 1, because if our base is 1, 1 to any power would just be 1. We're not really seeing any change there. The domain of a function of this form is all real numbers, because any numbers are available to substitute in there for x. Positives, negatives, rational numbers. We're just more used to seeing positive exponents there. Here's some examples of what exponential functions would look like. So you're seeing here for an example 2 to the power of x, or 1/3 to the power of x. So those are just some examples with numbers instead of letters, showing you what it would look like. So we're going to get started with example 1, graphing the exponential function of f of x equals 2 to the x. And the way I like to show you starting off with the graph for the first time is to make a table. So I'm going to go ahead and make a table of x and y values. And not just based on the definition, I could even just try out some numbers, but we can put in positives, negatives, rational numbers. So if I go ahead and maybe start with something like -2, then -1, 0, 1, 2, and maybe that'll give us a kind of a picture of what this would look like. So when I substitute these numbers for x into my exponent, it would be raising this base 2 to that power. When I raise 2 to the -2 power, so just some work off to the side here, I would have to use the property that would change this to the reciprocal, and I would get 1/4. When I use -1 as a power, I would get 1/2. 0, anything to the 0 power is 1. 2 to the first power is 2, and 2 squared is 4. So that gives us some numbers or some points to start off with. So let's go ahead and make a graph. And if I plot my points, negative 2 1/4, negative 1 1/2, 0 1, 1 2, and 2 4. And hopefully this shape or curve looks familiar to you from when you graphed exponential functions in the past. Before I draw this in, something you might want to think about, I know I already drew this in, but something to think about as you're kind of connecting the points. Am I actually going to go to the negative or end up in quadrant 3, so the negative part on the y-axis? And I want you to think about if is there any value you can substitute in for that exponent that would actually provide you with a negative y value. So 2 to what power would give you a negative? And that's what I kind of want you to think about. Because you'll see here in the table, if I raise 2 to negative powers, I still get positives, just reciprocals. To the 0 power is a positive, and I put in positive numbers, I get out positives. So it doesn't really look like there's a way to actually get a negative output or a negative y value here. So hopefully you can kind of see that there is an asymptote that's formed there, kind of representing the end behavior of this curve. Noticing that the graph is going to approach the x-axis but never actually cross it, because we're not going to get any negative values. The other thing we're not going to get is a 0 as an output, because 2 to what power equals 0? So 2 to question mark, or x, equals 0. And you can try out some numbers, but you're going to notice that you actually never see this happen. So you're never going to see this curve actually hit the axis. Now, there are ways to transform this graph with reflections and shifts, left and right, up and down. So we are going to see some of that happen where we may cross an axis, but that's not going to be when it's just a base to the variable of x. It'll be added or multiplied by something in order to see that happen. So some properties we can review that you can see represented in this graph are listed here. If you could take a moment and please copy these down and add them to your notes. So properties of f of x equals a to the x, where a is greater than 1. The domain you see is all real numbers. The range is all real positive numbers. So you're noticing there's no negatives. No x-intercepts, but there is a y-intercept at 1. There is a horizontal asymptote at y equals 0, and you may want to write there that that's the same as the x-axis. This curve is always increasing, and it is also 1 to 1, something that we talked about yesterday. So you can kind of apply that understanding. 1 to 1, meaning that, well, one way to check it would be that it passes the horizontal line test. So make sure you get those properties written down. Notice this is a generic list of properties for when the base, or the a, is greater than 1. So let's look at another example of when our base is between 0 and 1. So we're not going to look at negative base, but when our base is between 0 and 1. Alright, so our next example is to graph f of x equals 1/2 to the x power. So same way to start off the question. I'm going to go ahead and just make a table of values. And I'm just going to go ahead and choose the same x values, -2, -1, 0, 1, and 2. If you were making this table on your own, you really could choose any value you want to for x. My reason in making this choice is to try out some negatives, some positives, and then also 0. So when I raise a 1/2, and just again some work kind of off to the side here, to the -2 power, in order to change that to a positive exponent, I would use the reciprocal, and it would change that to positive, and you're going to get a result of 4. So again, the negative exponent is just causing that reciprocal to happen. So here I get 4. If I raise 1/2 to the -1 power, I get 2. Anything to the 0 power is 1. 1/2 to the first power is 1/2. And 1/2 squared is 1/4. So let's go ahead and plot these points and see what this looks like. Okay, so negative 2, 4, negative 1, 2, 0, 1, 1 1/2, and 2 1/4. Okay, so hopefully you're seeing kind of the similarities and then maybe even some of the differences between example 2 and example 1. Noticing that we still have that intercept at 0, 1. And it almost just looks like a reflection of the graph of 2 to the x. So hopefully you kind of notice that. Also, if you were to trace over this graph, you notice that it is a decreasing curve instead of increasing. So another list of some properties I'd like for you to copy into your notes would be the properties of f of x equals a to the x when a is between 0 and 1. So this would be when you get a base that is a rational number that is between 0 and 1. We're noticing the domain is all real numbers, range is all real positive numbers, no x-intercepts, a y-intercept at 1, y equals 0 is your horizontal asymptote, or that's the same thing as the x-axis, and it is decreasing and also 1 to 1. So make sure you take a minute and copy those properties down. And then just to kind of finish up our notes, we're going to do example 3. And this is going to be to take a graph like we did on example 1 and apply some transformations to it. So we're supposed to graph f of x equals 2 to the negative x minus 3, determine the domain, range, and horizontal asymptote. And all those things, if you'd like, you can determine after the graph. Some of them might be helpful to consider before. What I'd like you to start by thinking about is that you can use the idea of a parent graph. So I'm going to use a parent function of f of x equals 2 to the x, and that's the one that we did in example 1. The negative in the exponent is going to cause a reflection. And if maybe you're not sure what kind of reflection, we can substitute some values in to be sure. And then the minus 3, just be careful the way you write this. You want to make sure that it's clear this minus 3 is not in the exponent. It is after, kind of outside of. So that would be your shift down 3. If the minus 3 was inside our exponent, it would actually be our left and right shift. So one thing you can do is make a table. What I would like to do is actually just try and shift my parent graph. So I'm going to start by drawing the parent graph just with a dashed curve, using some of those points that I graphed in example 1. And then I know I haven't necessarily written what kind of reflection is happening yet, so I want to show you that with at least one of the points so we can get an idea of what's happening. So again, to start with the same points that I saw in example 1, what was it? Negative 2, we had a fourth, negative 1 was a half, 0, 1, 1, 2, and then 2, 4. 2, 3, 4. And this is f of x equals 2 to the x. So just making sure that you understand this is not my actual final answer. This is the parent graph. Now, any of your questions today, you can use a parent graph to help you graph it. Say this was 3 to the negative x minus 3. I can start by graphing just 3 to the x and then applying the transformations. If this was 5 to the negative x minus 3, I can graph f of x equals 5 to the x first and then apply the transformation. So you can start kind of maybe not necessarily with the parent graph, but kind of like a foundational starting graph if you'd like. The other option is always just to make a table of values. So maybe even just to start over here, we can start to see what happens with the graph, what kind of reflection it has. So if I take the x value of -2 and I actually substitute this into my equation, I'd have 2 to the -2, which would become 2 to the -2. It would really just be a +2. So this would become 2 squared, which is 4, minus 3, and that would give me a value at 1. So for this new curve, at -2, I'm now at 1. Oh, I apologize. Wouldn't it be at -1? Because this would be, no, +1. Sorry about that. So this would be 2 squared minus 3, and it would be at 1. If I found an additional point, like maybe -1, this would be 2 to the -1 minus 3. So this would be 2 to the +1. And now I'm down at -1. And if I put in 0, 2 to the 0 is 1. 1 minus 3 would put me at -2. If I put in 1, it would become -1. So this is where I'm going to start getting numbers that maybe aren't as nice. If I do 2 to the -1, that would be a half. So if I do a half minus 3, I'd be at -2.5 or -2.5. And then if I put in 2, let's see, it would be 2 to the -2 minus 3. And that would be a fourth minus 3. And we'd be at -2.75. So I'm really hoping that you guys would be at a point where you're either going to do the table or you're going to use a parent graph, not do both. I just figured for this example that it would be helpful to see both. If I went ahead and plotted these points, let's see, at -2, I'm at 1, -1, -1, 0, -2, 1, -1, 2.5. And at 2, I'm at -2.75. 1, 2. Also, you need to consider the kind of shifts that are happening. If I had a horizontal asymptote for that parent graph of 2 to the x on the x-axis, it would have shifted down 3. And that's why we're going to kind of see the points at -2.5, -2.75. At -3, we are going to have our horizontal asymptote. So you're going to see a shift down 3. Now your horizontal asymptote is not going to move if you shift to the left or the right. It will only move if you shift up and down. So you're noticing the shift down 3. And then if I try my best to draw on this curve, again, hopefully you can kind of discover what the reflection was here. It looks as though there was a reflection over the y-axis. So if you're going to see a negative in the exponent, you're going to see a reflection over the y-axis. A negative, say, out in front of the 2, if you there was a parenthesis maybe and then a negative in front of that, that would be over the x-axis. But I'm not sure if you'll see a whole lot of those. Just remember that your exponent applies directly to the base and not to whatever's in front of it unless it's in a parenthesis. So 2 different approaches, maybe using a shift and transformation or using a table. I don't feel like either way really takes a whole lot longer than the other. If I wanted to straightforward just do the reflection and the shift, let me show you how to do that. If I took this point on the original kind of parent graph and I reflected over the y-axis, I would be here and I went down 3. 1, 2, 3. So that's where you're seeing that point come from. And then here, if I go over the y-axis and down 1, 2, 3, this point is on the y-axis, so it won't reflect over, but it goes down 3. this point would go over the axis and down 3, and this point goes over the axis and down 3. So hopefully you can see that. Excuse me. So hopefully you can use either technique to help you do some of your graphs today. And that is it. So hopefully that was helpful to you. You can go back and rewatch if you need to get some of that information, and you can use additional examples in the book to help you if you get stuck.